In this video, we're going to look at some exam questions on the fundamentals of waves, so transverse and longitudinal waves, the properties of waves and their equations. Speed equals frequency times wavelength, and period is 1 over frequency. Pause the video to do this question. Press play once you've done it. You should have now done this question, so I'm now going to go through it. Please mark and correct your work as I go through it. So if the bar is hitting the water more times each second, that means we're going to have a higher frequency. Because what's the definition of frequency? Say your answer to the video. The definition of frequency is the number of waves per second. So if the bar is hitting the water more times each second, there are going to be more waves produced each second, which will increase the frequency. How can the frequency of the water waves in the ripple tank be measured? Well, if frequency means the number of waves per second, then what we're going to need to do is measure how many waves pass a point each second. So a good way to do that is to time how long it takes for 10 waves to pass a point. Now, frequency means the number of waves per second. So if we do our 10 waves divided by that time, that will give us the frequency. So for example, if it took 2 seconds for 10 waves to pass a point, then 10 divided by 2 will give 5 waves per second. If it took 5 seconds for 10 waves to pass a point, 10 divided by 5 is 2, which means 2 hertz, 2 waves per second. So if we do the number of waves divided by how long it took for those waves, that will give us the frequency. And finally, for question C, we want to work out the period. So we need to write the equation. Period is 1 over frequency. And we substitute 1 over 5, and that gives 0.2. And the units for period are seconds. Pause the video to mark and correct your answer. Press play once you've done that. You should have now marked and corrected your answer. So let's move to the next question. Pause the video to have a go at this question. Press play once you've done it. You should have now done this question. So a rarefaction. So a compression is the area of high pressure and the rarefaction is the area of low pressure. So this here that I've highlighted in yellow, that's the compression. This is a compression. This is a compression. And then in pink, I'm going to highlight the rarefaction. So the rarefactions are the area of low pressure, which are halfway between those compressions. So the center of a rarefaction is therefore going to be K. Distance of one length between them. So if you go from a compression to a compression or from a rarefaction to a rarefaction, that will be one wavelength. It needs to be from a compression to the next compression or from a rarefaction to the next rarefaction. So for example, the distance from here to here would be one wavelength. Also, the distance from here to here would be a wavelength. In the diagram, you have positions L and M, which are both compressions and are therefore one wavelength apart. And finally, to make a transverse wave, you need to make sure that the oscillations are perpendicular to the direction of energy transfer. So the oscillations are perpendicular to the direction of energy transfer. That is the definition of a transverse wave. Now, how can we make that happen in this diagram? Well, in this diagram, what direction is the energy transfer in? Say your answer to the video. Well, the energy transfer is horizontal, or you could say to the right, or you could say left and right. So the oscillation is going to be perpendicular to that, so that will mean up and down. So if you've said up and down, that would also be correct in this context. So either say the oscillations are perpendicular to the direction of energy transfer, or the end of the stretch string should be moved up and down. Pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to read this information. Press play once you've done that. You should have now read this information. Pause the video to have a go at these questions. Go back in the video if you need to refer to the earlier part. Press play once you've done it. So you should have now done these questions. So firstly, for part D, we have an anomalous result. What is an anomalous result? Say your answer to the video. So an anomalous result, or an anomaly, is a result which doesn't match with the rest of the results, which often means that something has been done wrong. There's been an error which has been made. So here we need to try and spot what the likely cause is. So if we go back to the data and have a look, the data shows us that 2.2 is less than all the other readings. So we seem to have a reading which is less than all the others. So to get a reading which was less than all the others, well, not resetting the stopwatch to 0, that would give us a longer time. Starting the stopwatch too soon would also give us a longer time, and timing more than 5 echoes would also give us a longer time. So the only one which would give us a shorter time is timing less than 5 echoes. Part E, we need to calculate the mean value of the time, ignoring the anomalous result. So we therefore need to calculate the mean of 3.1, 2.7, and 3.2. So we add them together and divide by the number of readings. You're always allowed to use a calculator in physics. So 3.1 plus 2.7 plus 3.2 divided by 3 gives exactly 3 seconds. You need to include units. They've already been given in the question, so we can just write the number 3. Question F, we have the distance between the student and the building, and the sound is going to go from the student to the building and back 5 times. So we have the student, we have the building, and the distance from the student to the building is 75 meters. But the sound is going to go there and back, and there and back, and there and back, and there and back, and there and back, probably along the same line. So I've just gone down because I wanted you to see every single arrow. So how many times has it traveled 75 meters? Say your answer to the video. It's traveled 75 meters 10 times. 75 times 10, 750 meters. So for part G, we need to calculate the speed of sound. So to calculate the speed of sound, we need to do distance divided by time. So we do speed equals distance over time. In part F, we saw that the distance traveled altogether was 750 meters. And in part E, we found that the average time for the 5 echoes was 3 seconds. So we do 750 meters divided by 3, which gives 250 meters per second. And finally, the value turns out to not be very accurate. So 2 changes that would improve the accuracy. So we need to do things that will give us less error. And the best way to do that is to take bigger measurements. The bigger the measurements, the better. That's just a general rule across all practicals. If you can take bigger measurements, your answers are going to be more accurate. So 2 things that we can do. 1, we can increase the distance from the students to the wall. So they could be 100 meters instead of 75 meters, for example. So increase the distance between students and the wall. That will increase the distance and will take the time for the echo to be longer. And then also we can increase the number of echoes that we time. So we could, instead of timing 5 echoes, we could time 10. So time more than 5 echoes. So remember, the general rule for getting more accurate data is take bigger measurements across every single area of physics. Pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to try this question. Press play once you've done that. You should have now done this question. So one quantity that's the same for both ways, well, they both have the same wavelength, which also means they both have the same frequency, assuming that they have the same speed. Now, we don't know for sure that they have the same speed. We're not told that, so therefore the correct answer should just be wavelength. So I can see that because I can see that both repeat after the same amount of time. You can also see the distance from a peak to the peak is the same for both. A quantity that's different for the two waves, well, their amplitudes are different. So this one has an amplitude like that, whereas this one has an amplitude like that. So their amplitudes are different. Which type of wave is not transverse? Well, you're meant to know that sound is a longitudinal wave, and all the electromagnetic waves are transverse. Now, you may not have studied the electromagnetic waves yet, but just so you know, the electromagnetic waves are radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma. Let's see if you can do that now. What does R stand for? Radio. What does M stand for? Microwave. What does I stand for? Infrared. What does V stand for? Visible. What does U stand for? Ultraviolet. What does X stand for? X-ray. And what does G stand for? Gamma. So those are the electromagnetic waves. So all of those are transverse. Sound is longitudinal. So you've got to know that. And the next diagram shows something called diffraction, which you may not have learned about, but you don't need that to do the question. The question wants you to find the speed. So speed is frequency times wavelength. You're told that every second, 8 waves pass through the gap. So if there's 8 waves every second, that means there's 8 waves per second. That means the frequency is 8 Hertz. So we have a frequency of 8, a wavelength of 0.015. We do 8 times 0.015, and that gives 0.12. What are the units for speed? Say your answer to the video. The units for speed are meters per second. Pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to have a go at this question. Press play once you've done that. You should have now had a go at this question. So the first part's interesting. It needs you to remember that for compression, you need 2 forces in opposite directions, and automatically they are going to be the same size. So you're going to have a force downwards on the spring. So the mass is pushing down on the spring, and it needs to be the same length as the force upwards. So the idea is that the spring is just sitting there. You put the mass on top of the spring. That mass pushes the spring down. But because the spring gets pushed down, the ground also pushes up on the spring as the spring gets pushed down. So those 2 forces are going to be equal and opposite. For question B, the smallest spring constant. So this one's actually a little bit tricky because you need to really think about what spring constant means. So pause the video and write down what you think a spring constant is. What is a spring constant? What does spring constant mean? So you should have now written down what you think a spring constant is. So a spring constant, you may have written down, it's how stiff the spring is. That would be correct. But what does it mean numerically? So what does it mean if I say that the spring constant of a spring is 50 newtons per meter? Pause the video and write down what that means. You should have now written down what 50 newtons per meter means. So 50 newtons per meter means that the spring will extend or compress, stretch or squash, 1 meter for every 50 newtons of force applied. So that means if you were to apply 100 newtons of force, how much would the spring be extended? Say your answer to the video. Well, if it's going to extend 1 meter for every 50 newtons, that means 100 newtons, which is 2 lots of 50, will extend it 2 meters. What about if you were to apply 10 newtons of force? How much would that extend it? Say your answer to the video. Well, 10 newtons is 1/5 of 50 newtons. So what's 1/5 of 1 meter? 0.2 meters. So that's what spring constant is. So when we look at these graphs, we need to find the one which tells us the smallest amount of force needed to extend by a certain amount of meters. So if we have a look at these diagrams, they all apply the same force. So in all the diagrams, 8 newtons has been applied altogether. Now, the one which has stretched the most for that 8 newtons is C. So that's the one that's kind of the least stiff. You've applied the same force to all 3, but C has stretched the most. That means it's the least stiff. It has the smallest spring constant. Which one has the biggest spring constant out of A, B, and C? Say your answer to the video. The one with the biggest spring constant will be B, because B experiences the same force, but only changes height slightly. It has the smallest compression. So the one that compresses the least has the biggest spring constant, and the one that compresses the most, C, has the smallest spring constant. The bigger the spring constant, the harder it is to stretch or squash. The smaller the spring constant, the easier it is to stretch or squash. Pause the video to try this second part of the question. Press play once you've done that. So you should have now done this question, and hopefully now you can see how this links to waves. So it's a bit different from a wave. We have an oscillation instead, but the fact that the spring oscillates, it bounces up and down, so this toy bounces up and down, that's very similar to a wave. In a wave, you have oscillations as well. You have this back and forth motion. So the maths ends up being exactly the same. So for question C, how many times each second, that means frequency. So you've been given the frequency, so the answer is just 1.25. So you're told the frequency is 1.25 hertz. That means it's going to oscillate 1.25 times per second. Part D, calculating the period. So period is 1 over frequency. So we use the same equation as we do in the waves topic. 1 divided by 1.25. It's a calculator, and that gives 0.8 seconds. For part E, you need to remember the equation for elastic potential energy. So elastic potential energy is half times spring constant times extension squared. You're told in the question that the spring constant is 7. You're told that it increases in length from 0.05 to 0.25. So that means the extension is the change in length, which will be 0.2. Don't forget to put the squared. That's very commonly forgotten. So we're doing a half times 7 times 0.2 squared, which is 0.14 joules. Pause the video to mark and correct your answer. Press play once you've done that. You should have now marked and corrected your answer. Pause the video to do this question. Press play once you've done that. You should have now done this question. So remember, for part A, the amplitude of a wave is not the whole distance from top to bottom. It's not the distance from top to bottom. That is not the amplitude of the wave. The amplitude of the wave is if you imagine equilibrium line down the middle. So that's where the thing would be if there was no wave, so just the flat surface. The amplitude is from the middle to the top, or from the middle to the bottom. So therefore, the one that shows the amplitude is K. The bar now hits the water fewer times each second. So just like earlier, that's now going to decrease the frequency because there's going to be less waves per second. How the wavelength can be measured accurately. So the way to do this accurately is you have to measure over several waves. So you would measure the length of usually 10 waves, then divide this by 10. This is because if we take bigger measurements, we're going to be more accurate. So it's always better to take the biggest measurement possible and then divide by how many waves you measured over. Finally, how does the speed of these water waves compare to a typical speed of a person walking? So that means the first thing we need to do is work out the speed of these waves. Before we can do that, we have to change the wavelength to meters. So 1.2 centimeters is 0.012 meters. I divided by 100. The frequency is 18.5 hertz, so I don't need to do anything to that. So then I do speed is frequency times wavelength, 18.5 times 0.012. So 18.5 times 0.012 is 0.222 meters per second. Now you need to know the typical speed of a person walking off by heart. So the typical speed of a person walking is around 1 to 2 meters per second. So between 1 and 2 meters per second. So therefore, the speed of these water waves is way less than the speed of a person walking. So the speed of the water waves is less than a typical person's walking speed. Pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to try this question. Press play once you've done that. You should have now done this question. So what's the wavelength of the water wave? So I'm going to go from this peak to the next peak, and I can see clearly that that's 4 centimeters. The amplitude, we have to be careful. We have to go from the middle to the top or from the middle to the bottom. So if I go from the middle to the top, I can see that that is 3 centimeters. And finally, for question C, if it's 12 waves in 4 seconds, I want to know the frequency, which is the number of waves per 1 second. So divide 4 by 4 to get 1, divide 12 by 4 to get 3 waves. So if there's 12 waves in 4 seconds, there'll be 3 waves in 1 second, which means the frequency is not just 3, we have to say 3 hertz. If you've not put units, your answer is not fully correct. You need to add units. Please pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to try this question. Press play once you've done that. You should have now done this question. So for question A, it's just resultant force equals mass times acceleration. That's Newton's second law. So for B, we have to use that, but we're going to have to first work out what the resultant force is. The common mistake here would just be to use 2.7 or 1.5, but that's not correct. The resultant force is going to be the difference between 2.7 and 1.5 because they're acting in opposite directions. So 2.7 minus 1.5 is 1.2 newtons. So the resultant force is 1.2 newtons. So now I can use the equation. So 1.2 equals the mass, which is 0.75 times A. So A is 1.2 divided by 0.75. 1.2 divided by 0.75 is 1.6. And what are the units for acceleration? Say your answer to the video. Units for acceleration are meters per second squared. Pause the video to mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. Pause the video to do this question. Press play once you've done it. You should have now done this question. So I'm going to go through it. So if the trolley is pushed and released, the trolley is going to be oscillating like this. Now, that's going to send a wave along the cord. So that's going to send a wave in that direction. So notice we've got the wave moving in this direction, and we've got the oscillations going in this direction. They are perpendicular, so therefore this is a transverse wave. So to explain that, you need to say it's a transverse wave because the oscillations are perpendicular to the energy transfer. So your explanation is really the definition of transverse wave. So they're transverse waves because the oscillations are perpendicular to the direction of energy transfer. If we want to have a lower frequency, that means we need to kind of slow down these oscillations. We need less oscillations per second. There's two things we could do. We could increase the mass of the trolley, because if we increase the mass of the trolley is going to have more inertia. It's going to be harder to accelerate. It's not going to go as fast. We could also decrease the spring constant. That's decreasing the stiffness of the spring. Now, the reason that works is if we want a lower frequency, we want the oscillations to have a lower acceleration. So if we think about the equation, F equals ma, we rearrange that to make acceleration the subject, it's resultant force over mass. Now, we've already said that we can increase the mass of the trolley, because if we increase the mass of the trolley, what's that going to do to the acceleration? Say your answer to the video. That will decrease the acceleration because acceleration is inversely proportional to mass. You can see that from the equation. But if we decrease the spring constant, that can also work, because if we decrease the spring constant, we have the equation force is spring constant times extension. which means that the force is proportional to the spring constant. So if we decrease the spring constant, we therefore decrease the force. And from Newton's second law, resultant force and acceleration are directly proportional. So that means we decrease the acceleration as well. So just to summarize that, acceleration is proportional to resultant force, but inversely proportional to the mass. Resultant force is equal to the spring constant times the extension. So therefore, we can decrease the acceleration either by increasing the mass or by decreasing the spring constant. And both of those would give us a lower frequency. Please mark and pause the video, mark and correct your work. Press play once you've done that. You should have now marked and corrected your work. I hope this video was useful. Please like and subscribe for more videos on GCSE physics.